We're talking about Erlang distribution again. This is a long-running project we are working on. Currently, we are working on, I have to mention this, like this is funded by the EU, so your tax money at work. So, Erlang distribution. Yeah, this is like weird formula, and you basically get these different statistical distributions, and I think we know this guy. So let's dive into it. Or maybe not. Maybe talk about the other Erlang distribution. What does it give you? It's a transparent distribution protocol, and why do we want to use it? Because of course you can like implement protocols in Erlang pretty easily, do your own stuff, run TCP sockets between your nodes or whatever. But what you get extra for the transparency, I mean, you don't have to care about like encoding and decoding and stuff like implicitly. But in addition, you get linking and monitoring, and you can like pass a bit from one node to the other, send it through, and it actually would work transparently through the network. And we think this is some really important extra value for building distributed application. And that's why instead of running our own layer of whatever protocol, we are ongoing working on actually fixing the built-in distribution. So why does it need fixing? It has following problems. The default is fully connected mesh. It doesn't scale because fully connected meshes don't scale well. You have n-square connections that kind of like floods at some point. It overflows. There's workarounds, but which are only workarounds, and some parts of the which run on the Erlang VM actually expect the fully connected mesh, like the global process registry. So this needs to be touched too eventually. So with this, I hand over to Adam, who will tell you about the UDP distribution prototype. That is one of the steps.
Some of the work we're doing, we experiment with new things. We want to try things out, and using UDP for distribution instead of TCP was one of these things. So we wanted to solve head-of-line blocking. This was 1-2 years ago. We had a TCP prototype implemented where we did this, and we wanted to experiment with other ways where UDP was one of them. So instead of having long-running sessions like connections, TCP connections, you would just flood a bunch of UDP packets, and things like head-of-line blocking wouldn't be a problem anymore. We also wanted to do it so that we could basically see what's involved in building a custom distribution implementation, what are the pitfalls, how does this API from OTP work, and so on. And we want to learn in general about networking and Erlang so that when we build more solutions later, we have some experience doing different types of distribution implementations. So building an Erlang distribution is actually quite complex. This is just some sequence diagram I was trying to draw just to figure out like how does the API towards the kernel work when you build an Erlang distribution implementation, a custom one. And it's pretty complex, but I'll try to explain it a little bit more like simply, and you can get a feeling for what's involved in building a custom distribution. So you have your applications running on Erlang VM, normal Erlang applications, libraries, stuff like this. You have the kernel. So that's the part of the VM, like the very central part that starts very early and maintains some of the core Erlang features in the running VM. And this is where you hook in your distribution behavior. So if you override the default one, you can make a module called, let's say, mydist, and then it's up to you to implement the transport protocol. So by default, with Erlang distribution, you have TCP, if you use it just out of the box. And this is implemented in the VM, so it's very efficient and very nice. When you implement a custom distribution implementation, you actually replace it with Erlang code. So kind of like kernel space and user space in an operating system, it's the same here. You go now into Erlang land, and we use then Gen UDP, the UDP socket library in Erlang, and then we build stuff on top of this, and then we head out on the network and talk to other nodes. I'm going to rush through these slides a little bit quickly, so don't bother with all the details. But roughly, the current implementation of the TCP example in Erlang that comes with OTP and our UDP implementation kind of works like this. So you have the Erlang nodes, you have the kernel and all the stuff around it, and then you have your custom distribution implementation. And that has to run on both nodes so that they can actually talk to each other on the same protocol. And when you start the nodes, you start a acceptor process that basically listens for incoming connections. So a node connection can be initiated from either node, right? So if you do an RPC call, or if you tell the net kernel directly to connect to a node, you have to be able to reach that node somehow. So there's an acceptor process running on both nodes. And once on the very left side in the top left corner, if you want to ping the second node from the first one, you talk to it ends up in the kernel, which tells you distribution behavior, connects to the acceptor on the other node, synchronizes with the kernel, spawns a connection process on both sides. And then after this, the kernels actually do a handshake. And this is not something you have to do in your own behavior implementation, so you can hand this off to a module called distutil, which does all the Erlang handshake stuff for you. And this includes things like checking sockets, maybe checking some Erlang version compatibility and things like this. And you just have to take care of transporting that data back and forth. And once the handshake is done, you spawn a input process, and you transform one of the processes to an output process. And from that point on, you have basically a bidirectional connection. And so the input process takes care of getting input from the other side, and the output process takes care of sending it. And obviously, they send to each other's counterparts on the other side. So to summarize, there's one acceptor process per node. We have a separate UDP listening port for the acceptor part, where we listen for any incoming node connection. And then for an active node connection, we spawn two processes, one per output, one per input. And in addition to this, I didn't show it, there's also a tick process that keeps the connection alive by sending tick messages. So you can bypass like firewall things and keep ports open. And all of this is in the custom implementation. It's basically based off of the example TCP implementation in OTP. We could have done it with one process. We could have done it with 200 processes. It's completely up to you when you make this implementation. And we also use the Erlang port mapping daemon to tell the other nodes which UDP port we're listening on. Normally, the port mapping daemon works with TCP, but we abuse it for UDP ports as well, and that works. So. Right, so let's show a short demo of how this works.
Differently colored, so you cannot mix them up. And I'm be running basically a similar line in every window. I start on the Erlang node. I set the path into the thing where we actually built it. So that's not important detail. The important thing is then we call protodist. And pass it the name of the module which implements our part of the UDP distribution. We set the cookie and we set the node name. That's normal distributed Erlang setting. So I run this here and I get one node named foo, and I have this pre-typed here also with another node name. So we have nodes foo and bar. Bar is pink, foo is green. And let's go into one of the nodes and ping the other node. Foo at Venus. So if you get a pong, that worked. So this went over UDP. So let's do something more complicated, because this was like a tiny packets and doesn't need to chop up into multiple UDP packets. So let's do an RPC call on this node, for example. We run the RPC call, so we run a remote procedure call on the other node, bar at Venus, and we run Erlang byte size and pass it an argument where we pass a binary, and let's have a bunch of 1000 0 bits. And then I need to add a timeout. Let's make a long timeout, just to be sure. And so this should be running on the pink node now, via UDP. So we got back 128 bytes. That's 1024 bits. So this is correct. Seems to work. So let's have a look at the wire. For that we use Wireshark. I need to find the loopback interface because this is all local on this node. And we want only UDP packets, so we don't get so much traffic. And then we already see this packet here. So can you see this? I hope it's large enough because I can't. So we see like these small packets going, like 5-byte packets going on. So let's make a larger binary. So we actually get a bunch of packets, like let's send 10,000 0 bits. So this also works. And you see there's a bunch of UDP packets here. And you see these in the content of the packet. You see like there's the header and then lots of zeros, which is our value actually. And in Wireshark you can follow a stream. So I need to find my stream again. So you can actually basically say, yeah, follow this UDP stream. So it basically gets to and fro port, and then you see basically, and we display it as ASCII. So you see ticks, which actually have the atom tick in them. So you see tick as text, and then there's like big stuff going on. That's the zeros that we transmit, and the answer back, and then there's another tick down here again. So just as a proof that this runs over UDP, and then you can, I can increase this until it breaks. So this chops it up, and I don't know, I didn't try this out. Yeah, I think it works large enough. So that's a lot of UDP packets now.
And there's no packet loss on localhost, hopefully, yeah. So that's fine. Over network would be a different thing. Actually,
there is, because it's a tiny, the buffer on localhost is very small, and you can actually overrun it. And because nobody wants to do UDP on localhost, it's kind of a weird implementation detail.
And the other ASCII stuff you saw, like all the noise, was basically encoded Erlang terms trying to be printed as ASCII by Wireshark. We were thinking, okay, we've done this. We looked at the implementation of the API in OTP, and what's the next step, basically. And since we want to experiment more with distribution, we thought maybe it's a good idea to take this slightly complex API and write the behavior on top of this, so that if you want to make a new distribution transport, you just have to implement some nice callbacks. And you can take care of all of the transport low-level details like socket and such, and you don't have to care about this whole handshakes and processes and stuff that has to happen. So since these prototypes we did so far was quite similar, we thought, okay, let's take all this complexity, make a behavior out of this, and how would we do this? How would such a behavior look like? And what are the valid process models, or what are good process models for such a behavior? The examples, they all use like 3 processes per node connection. So if you have 3 nodes in your cluster, each node would have 1 acceptor process plus 2 times 3, so 6 other processes. Maybe there are other models. Maybe you have a transport where you don't need any process at all because there is some other hardware driver that does this for you. Maybe you want many processes. Maybe you want to multiplex over many sockets, stuff like this. And actually, is it easy to do something that lets you replace the pure transport layer and just says, okay, you implement the socket API and you replace it with UDP, TCP, or your own socket implementation, and then keep all the process model stuff generic? So we were looking into this. So the current state is that there is a custom distribution API exposed in OTP 20, and it's based on the eternal implementation of TCP, and it exposes like all the different kind of endpoints or hook points where you want to change the actual distribution behavior. So there are some challenges to using this kind of, let's call it low-level API. One thing is that it starts super early. So Erlang distribution starts almost exactly when the node starts. So there are things like, there's no kind of built-in supervision tree, like a proper OTP one, but more some links here and there between processes. And errors can sometimes be hidden because there is like not proper I/O already, and some of the links, when they go down, the errors are not printed in the nice way you're used to. Like if you crash a Yen server, you get a super nice stack trace and all the system events. This doesn't happen here, so it's a bit harder to debug. And rewriting all this code from scratch all the time when you make a new distribution implementation, it's nicer to have it encapsulated in a generic behavior. And the API surface is a bit fragmented, so there's a mix between callbacks, function calls back into kernel space, and message passing. So we want to also abstract all of this away into a more kind of functional API. So I already talked a bit about this. The existing process model is basically per node, you have an acceptor, and for each node connection, you have an input and output process. And there's also a tick process that takes care of sending the ticks. And this only happens when the pipe is idle. So if you don't send any actual data, you send a tick instead. And this is used for Erlang node liveness. So if a node monitors other nodes, you can see when they're down or when they're not accessible, and then send events to the system, and the process is running on that node, so they know that the node connection is down. And a new transport might require, as I said before, like different process models, and kind of it's an unsolved problem, let's call it, in the Erlang world, or I haven't seen a nice example of how to do this. So basically have a behavior with callbacks, but then you have some kind of dynamic process model underneath, which you can either tweak or change. So this is a challenge for us, finding a nice API, and I'll go a bit more into detail later why this is hard. So the plan for now is to implement a generic behavior that uses exactly the same process model as the example in OTP and our UDP implementation. And first encapsulate this, and then when we have that, we can then maybe move stuff that is done in the behavior in the custom distribution implementation into the behavior, or vice versa. Ideally, if you build a custom distribution, you would have a nice callback API, and then you could define your own process model for what you need in your transport. So hopefully we'll get there in the end. And the API we're looking at right now is a bunch of callbacks, basically, for the acceptor, for the output process, the input process, and the tick process. And take away all this complexity about message passing and linking to kernel processes and things when you make your behavior, and just make a module which implements all these callbacks, and then we deal with all the other stuff under the hood.
I think it's my turn again. So that was basically the more low-level approach, like bottom-up, to actually go take what's there and try to evolve it into something different. But we can also take a more high-level approach, like what if we, for example, don't have an acceptor process, so we actually are not called in, but we all call out, and we call into a kind of like cloudy thing where we implement whatever we need, the whole transport. We hide everything. So we don't do connections or UDP ports, or we hide all these things. So you basically have the kernel and your MIDIS module, and then you have an abstracted away like node registry, where because that's one of the things that you want to know, like which nodes can I talk to? What's the set of nodes? And then also on transport in the same like unit, hidden away, and probably also in addition some security policy, because if you want to scale this up, then security gets more interesting. Suddenly you have huge clusters, and you need to kind of like figure out, probably beyond having a cookie, if you have like a worldwide cluster of Erlang nodes, who is allowed to connect to your cluster and who not. And then, for example, you could do like totally different transports. So MQTT is a message passing protocol with PubSub, which scales pretty well to a lot of like devices. And you can map the node names and different messages and even process groups, if you want to MQTT topics, and use PubSub to actually interconnect the nodes and use MQTT as transport for the Erlang distribution. So you need some external infrastructure. You need an MQTT broker, or basically a tree of MQTT brokers between your nodes, but then you can have like easily 10,000 nodes. That's a small MQTT implementation. So that's the more high-level approach where it's like we abstract away a lot of things to use infrastructure, whatever.
We're approaching more worlds where we have heterogeneous networks. So we have different types of nodes, we have different network setups. You might want to traverse network borders. So a familiar example might be if you're running on a cloud service somewhere, you have a bunch of servers and you connect them all, and maybe you want to do cross-geo replication to another data center. So it would be nice to use Erlang distribution, but maybe the things that go over some node connections could be done in a local, nice, optimal way. Some stuff that goes over a global connection could be done in a different way. So this is kind of all long-term thinking. So the fully connected mesh is the current state of Erlang distribution. Basically, when you join a network, you as a node get actually a real TCP connection to every other node in the cluster. This doesn't scale for various reasons, but the most obvious one is if you just think about the tick message. So when you as a node want to know if all the other nodes you're connected to are alive, you listen for their tick messages. And if you don't get one, you can assume that node is somehow down or missing, or the network link is broken, or whatever it is. And then you can build a distributed system on top of this. So you can fix your amnesia database, or you can build it out of something else. However, as you add more nodes to this ring and you get these many-to-many connections or all-to-all connections, those ticks will basically multiply exponentially in your cluster. So every time you add one node, you get an exponential amount of more ticks going on all the time. And based on how you configure this, you might end up in trouble because now your system, all it's doing is just ticking and there's no space for traffic left. So we're looking at, for industrial applications is one example, but just doing some more mesh-like connections, which obviously scales very well. You just hook stuff up on the end and keep building and building and building. But you need some kind of routing here. And either it could be done on the Erlang level. You could build this manually, so you can have a custom TCP socket on each Erlang node talking to another node, and then you have a module that sends all the Erlang traffic. But then you don't get the nice Erlang stuff. You don't get like process messages, and you don't get the links and monitors. So obviously using Erlang distribution would still be cool. And then you could do this routing in the custom distribution implementation maybe, or you could even go even further and do it on the network layer. If you have a proper network that does nice routing and like on the Ethernet level and so on, level 1, level 2, level 3, you might not have to do it in Erlang at all, or you might tap into that at least. So custom distributions is something we want. And we want to basically research, can we do this and keep the topologies transparent to the application layer. So if you go into an Erlang node in this cluster and you type nodes, maybe you get a list of all the global nodes that are attached to this mesh. But in fact, you only have a physical connection to, let's say, 3 of them. But you don't need to know this as an application implementer. You can just say, I want to send a process to that node, or a message to a process on that node, and the underlying transport will just take care of routing it there. Transports can also be made transparent. So if you have heterogeneous networks where you have maybe UDP in some parts, TCP in others, SATP in yet another, and then MQTT in one corner, like the application doesn't really need to know about this as long as it looks like it works. So to do this, you need some way to represent like a virtual node connection. Either a way to hide it to Erlang, so that from Erlang point of view it looks nice and a full node group, or yeah, somehow you need to deal with this. And we think it can be done in a transparent way, so that you don't have to adjust your application, so that you can rely on the full power of OTP basically. So yeah, I was talking about how you could do this already on the network layer, and so Per will go in a little bit into Ethernet TSN and what this can bring us.
So this is kind of now something completely different, or rather one of the motivations we had looked at UDP, because with Ethernet TSN we can actually get the advantages of this new technology that's kind of like still in the making. Ethernet TSN stands for a new kind of Ethernet, and TSN stands for time-sensitive networking. So this is about hard real-time bounded latency on Ethernet. So you basically bounded latency transmission, so you know exactly how long your latency is. If you keep to your bandwidth, of course. there's always a price to pay. There's no free lunch here. You also get very super low transmission latencies. You have options for that. Can have like high priority packets cutting through other traffic very quickly, even interrupting other packets. And you can get actually reliable delivery of Ethernet packets. And that makes UDP much more useful because we kind of like don't have to deal with packet loss that much, because when it's very rare, then we can just do a node down, node up, and simulate that to the application that, yeah, you might have lost some data. But if this happens too often, that messes with, for example, with amnesia. Amnesia doesn't like it when the links go up and down regularly. And we have an ongoing research project, which is like kind of like long running, because we don't have so much time for it. We have one master thesis already spent on this. We want to have hard real-time processes for Erlang. So then you can have a distributed hard real-time application written in Erlang, or Elixir, or whatever other language on the Beam. We are also looking into PLC languages, which runs fully distributed and has hard real-time, basically properties across the network. So hard real-time means like it's really bad if you miss a deadline. There's a fuzziness because there's always only probabilities, but hard real-time means it's a real error if you're late. So if your data is late, if your action is late, it's too late. Usually something blows up and then it's really too late. So that's basically all the TSN standards. I don't want to go into a lot of details with them. Does this actually have a laser? Oh yeah. So you need time synchronization, so you synchronize time in network, that's PTP, like nanoseconds resolution. You need some hardware support in your Ethernet drivers, but most of the current Ethernet drivers have this. Then there's something about configuration. That's more for video. So this comes out of the video transmission stuff, like bandwidth reservation for video. Then you have like a bunch of standards. So the IEEE is very busy nowadays, so they were a little bit bored for a while because they didn't make new standards, but now they're cranking them out by the dozen. So they're really happy now. Lots of standards to make, so you can have cyclic queuing and forwarding. QBV, I'm going into QBV a little bit because it's a nice example of what can be done and how it actually works. That's basically scheduled traffic, so you schedule the traffic into time slots, and then you can guarantee that it arrives within the latency that you guarantee. And then there's frame preemption. That's more advanced things that you have basically high priority frames interrupting low priority frames and to block the thing. And then there's frame replication and elimination. That's the thing where basically on layer 2, if you send a UDP packet, for example, that gets translated into an Ethernet packet, and then it gets translated into multiple Ethernet packets that go different paths through the network, and on layer 2, basically before it even reaches the TCP stack, these packets get reunited into one packet. So that's the reliable Ethernet packet thing. So the automotive industry is behind this because they want to replace all the buses in the car with Ethernet. If you want to do drive-by-wire, you better make sure that your packets arrive. The other half of the basically industrial Ethernet conferences is like industrial transport systems, like in manufacturing, they are also replacing this by Ethernet. And that's our main interest here. So how would this work that you can actually guarantee latency? So Ethernet is a medium where you have, which is very asynchronous. Basically, you want to send a packet, you go out on the network, see if it's free. If it's free, you basically send out your preamble. You see if you have a collision in the preamble, because somebody else might have also seen a gap in the network, like, oh, there's started at the same time. And if there's no collision, you go on. But this is pretty random because you don't know who else is on the network sending what. So there's no coordination going on. And the way this is reached for time-sensitive systems is that because you have time synchronization, you can then agree, you can configure a time slot, like a regular interval of time, which you can then basically partition into different priorities. And they abuse virtual LAN IDs, which are used for other things also, for the priorities. So in this case, you have basically, we see 2 cycles, and in the beginning of each cycle, there's basically a slot where only virtual LAN ID 3 packets are allowed to be forwarded. And this is actually done by the switching fabric. The switch actually doesn't forward other packets. So you have actual hardware support on this. This is not software. It needs support in the switches that they forward this. And the switches also synchronized to each other, so everything is synchronized in the network. And then suddenly you have something, I mean, it's all in cycles because you have like synchronous protocols, and you implement asynchronous protocols on top of synchronous, like IP over ATM. ATM is a synchronous protocol in telecoms. You make IP over ATM. Now we do everything with IP, and now the people kind of like miss their synchronous stuff, and they implement synchronous stuff on top of Ethernet again. So there's a few little details that you need to make sure. If you basically have a packet on this gap here, which like blocks the network, like overlapping into the high priority zone, this is not good because it actually preempts the other packet from being sent. So if you cannot cut it off, so what you need to add as a little detail, you have a guard band. That's basically one maximum packet size where you don't send anything. So that's the price. Real-time always has a price in throughput there. And that's basically, you can buy like little tiny automotive switches that implement this. And we're actually working with this. And if you combine this with UDP and the Erlang distribution over UDP over TSN, then you can have this hard real-time or bounded latency distribution protocol. And I have a hunch that parts of this will also be showing up like in cloud environments eventually, because you can do other things, and there's some parts of the standard where you can see it's actually headed towards larger things also. So this might actually pop up not only in our world, but also in your world of non-embedded things. Summary you?
Yeah, I can do that. So, the current state is we have a work in progress generic distribution behavior that we're working on. We've gone down a few different paths of how we wanted API and the process model to look like, and that's why it's not done yet, but we're getting there. And also a huge thanks to the OTP team because they told us a little bit about the low-level details about the API, how to interpret it, and what it means, so we can get a better implementation. And basically, we're investigating these API alternatives. And in terms of TSN, what we are doing already is we're implementing a TSN switch with shorted path bridging that Per already went through a little bit. And what's cool is we're using Erlang for the control plane. So there is also Erlang on the switch itself to configure the hardware. I mean, once the hardware is configured, it will just do its thing in hardware, very efficient, very fast. But when you want to change things, it's a great use of Erlang because it's a nice language and fits very well into this semi-embedded space as well, and all the networking stuff. So for future work, we're looking at connection-oriented UDP. Maybe this makes sense somehow. There are a few different implementations out there. One example is Google's Quick protocol, which might actually be nice for Erlang distribution. We're looking at doing an MQTT prototype, so trying out this kind of virtual node membership, having some centralized cloud management of Erlang distribution to see where that leads, where we use these virtual node connections and try to see if it's feasible actually to hide this from the application layer. On the industrial side, we want to then run our ODP stuff over TSN and actually put this into production. So the router we're making, the switch, and the projects we have are about building industrial, basically manufacturing pipelines. So we're talking about a real factory with conveyor belts and machines moving and things, and we want to use Erlang all over the place, small nodes connected in a mesh to control this or look into this factory. So we have the switches, we have the Erlang boxes, we have embedded Erlang running on the GRIS board and so on, and then we want to basically put all this together and see where that leads us. And we're also looking at implementing real-time control prototypes. So this is approaching the whole space from a different angle, basically real-time Erlang, connecting Erlang close to hardware, ensuring real-time hard real-time guarantees and things like this, and how that could also be brought into Erlang in a transparent way so that you can write Erlang code but still achieve real-time robotics things and whatnot.
basically what we are also doing. We need some hardware to run this also, and some hardware to prototype this on. And we made the first version of this. It's the Gris board. You might have heard of it. That's the thing that's blinking on my neck here. I've written a little blinking light on it. But we now basically ran out of the first batch, and we are making a second version of the Gris board, which is basically evolution of this. So greatly improved in all kinds of things. The core selling point of this is that it runs Erlang on the bare metal. I mean for real. Like there is no operating system between the Erlang VM, which is, by the way, a full-blown Erlang VM, a normal Erlang VM, and the actual hardware. So if you go out into an if, then you immediately can write into the hardware registers. So you get very low latency between things happening on the hardware and things happening in your Erlang node. The new Gris board is a little bit larger. It has a little bit larger CPU, so it's actually capable of running Linux, because this one wouldn't be, or it would not be any fun at all. So we are working together with the Nerves team here, and we're putting special hardware on them for their crypto stuff, for the Nerves update. So we basically, in the future Erlang Ecosystem Foundation embedded working group, we will kind of like fuse this together, so you have basically more choices. You can run Nerves on this board, and therefore also have a board with nice user experience to get started with Nerves, because if you control the hardware, you can actually provide a nice user experience for embedded systems when somebody gets started, like from 0 to blinking light, not in like a few weeks, but in an hour, or even below an hour. So I demoed 0 to blinking light during a talk, so this works, like empty directory to this state here. This time we are using a system on module, so we actually have modular hardware. This is soldered on, so if anybody wants to make something, our own device with own sensors, you can actually easily reuse the system on module on a very much simplified baseboard, which only has I/O and sensors and actuators on it, and all the essential things that is necessary to run Erlang is on this system on module, which is like about this size. It's faster, it has more RAM, and we have here, this one only has Wi-Fi, and the new one also has Wi-Fi, Ethernet in addition, like Wi-Fi and Ethernet, because having Wi-Fi is cool, working Wi-Fi on an embedded system, but having only Wi-Fi has its limitations, especially during development. It's sometimes convenient if you just plug in and don't have to configure an access point or whatever. We ran a Kickstarter to basically finance the first production run. This was successful. We are fully funded. We reached all our stretch goals. We're really happy about that. So we're not only making the boards, we're making cases for the boards, and we also make a battery add-on. So a nice lithium-ion battery, which basically gets charged when you're plugged in and runs the board when the power fails. So you could add a photovoltaic cell and put it up a tree and run it 24/7 unconnected. I think that's about it.
Yeah. So
and you can pre-order it now.
Yeah. If you go to the homepage, there's a link to the Kickstarter, and there you'll find all the information about it, and also links to the pre-ordering if you missed the Kickstarter. So that was it from us. Thank you, and questions?
So have you considered using SCTP as a transport?
Yes, actually somebody else has done it already. I think Tristan Slaughter has a preliminary SCTP implementation using the new exposed UDP. Definitely this would be also one of the connection-oriented UDP implementations. The SCTP would definitely work and work well.
So if you have failures, a lot of parts of OTP assume strong consistency of global registries. Have you started taking a look at scaling that up across large geo areas and this kind of thing?
So that goes, but basically our thoughts in this direction go mainly into this like high-level approach where you have a separate node registry or have other means of doing this. I mean, in generally, if you really scale up and you expect you have a global node registry or a global process registry with which like unique naming, this is not going to scale, no matter what. So you have to go to groups. You have to go to process groups and send to groups. And that's actually one thing I want to explore, how we can plug into like something like PG2 or make a new API where you can then efficiently send messages to groups. And There's also thoughts in the UTP team that you might be able to send like a message to a list of processes in one thing, which you then could like pick up. And for example, if you have the MQTT distribution thing, this could be just like one message to a topic, and whoever listens to the topic is registered to this group gets the message. Because eventually what you want is like send this message to any logging server or to any whatever, and not like to this specific. So for our application, what we need is basically we need like concrete registry in like smaller areas of a larger network. So we have like islands where I really want to talk to this node and this process on this node, because I know this is an embedded I/O thing, and I actually want to see the value on this wire, this specific one. So for that we need it, but this can't scale. So we want like local, if it's local enough, because we only need this when it's local, and then if it gets more global, you need to kind of like give up something in the registry.
So on the UDP protocol stuff that you're exploring, have you looked at any of the existing game protocols? Because in the game industry, everything's UDP. It's all time sensitive, and it's a really well-tread ground where there's protocols where you say, hey, this packet has to get there, it has to be on time. This one, nice to have. This one, if it gets there, okay. Out of order, okay. If it fails, okay.
Yeah.
Right.
To be honest, no.
It's fertile ground, and I would suggest you take a look at some of them.
Because we have no idea of these protocols, we don't know them, and we didn't.
I mean, I did look a little bit at a few of them, and some of them have nice C libraries. So that was like the bullet point about Quick was more like, okay, it could be Quick, SCTP, or one of those ready-made game libraries, and whatever kind of fits the bill there. But it's all on the idea stage, so nothing concrete done.
When is this going to be ready? Because we work on systems like Rabbit, which use Mnesia, and the moment you scale out on wide area networks, that becomes a bit, Erlang distribution doesn't perform really well. So when can we expect this?
So I hope that the behavior API will be ready quite soon. Then you could build your own on top of this, but hopefully fairly easy. So that's our next immediate goal.
For like scaling Amnesia, what you want is some kind of buffering that basically you kind of pave over short outages in the network. Because if you run in a cloud environment, you see that the network is actually much more unreliable than you would expect. But usually it's short outages only. And you need to find a way to pave over those, like to hide those from Amnesia, because it doesn't like it. If there's lots of like node drops, that really confuses it.
That's fine. Okay, thanks. So we won't replace.
But you can do this on the distribution layer by kind of like buffering, reconnecting, and hiding it from the Erlang nodes, basically. And then it should work more reliable.
Cool. Thanks. All right, guys. Another hand for Adam.
Thank you.
Thank you very much.